Hello, hello, hello. In this worked example, we're going to consider a very practical problem, especially if you compete in the shot put. You throw a heavy object through the air and you want to know how far it's going to land from you. The range here, that's the figure of merit that's going to determine whether or not you win the shot put. And the thing that makes this problem a little bit different than the simple projectile motion range calculation that's done in your text is that we're going to take into account the fact that the ball leaves at starts its projectile motion at some elevation above the ground. And then we want to calculate how far it's going to go. So that's the problem. How do we solve it? Let's dig in. And because a shot put is a rather dense object, the drag forces that act on it are going to be very small compared to the force of gravity. So we're going to be able to an excellent approximation, neglect the effect of drag when we solve this problem. So in the particular problem at hand, we're told that the shot put leaves the shot putter's hand at an elevation 2 meters above the ground, traveling at a speed of 16 meters per second with a launch angle theta naught of 30 degrees above horizontal. And the basic principle, as is common to just about all projectile motion problems, is that we can separate out the motion into vertical and horizontal components. In the horizontal direction, the object's motion travels with zero acceleration. And so the horizontal component of the velocity remains constant throughout the motion, whereas in the vertical direction, there's a downward acceleration of 9.8 meters per second squared. And we can calculate the range. This quantity r is just going to be the horizontal component of the velocity, which we'll call v naught sub x, times the time of flight, t sub f. And by time of flight, of course, I just mean the amount of time that the shot put is in the air. Time zero starts when it leaves the shot putter's hand, and the time of flight is the amount of time it takes to get to this point where it lands on the ground. And V naught sub x is just 16 meters per second times the cosine of 30 degrees. Then we have our times the time of flight here, and the cosine of 30 degrees is, of course, the square root of 3 over 2. So the range is just equal to 16 times root 3 over 2 meters per second times the time of flight. Or more simply, of course, we can write this is just 8 times root 3 meters per second times t sub f. So answering the problem really just reduces to the problem of finding out how long the shot put is going to remain traveling through the air. So to solve for the time of flight, we just have to notice that we can write in this problem, again, in the y direction, the shot put is going to undergo accelerated motion in the downward direction of 9.8 meters per second squared. So the y coordinate as a function of time, just in general, we can write as its initial y coordinate plus the initial y component of the velocity times time minus 1/2 gt squared. And the flight is, of course, going to end when the y coordinate, we're calling y equals 0, is the ground level here. And if we agree to that, then the flight is going to end when the y coordinate ends up being 0. That's here. So what that means is, and I'm going to plug in the numerical values for y naught and v naught sub y. So that says that 2 meters plus the initial y component of the velocity is, remember, it was going at a speed of 16 meters per second and an angle of 30 degrees. So the sine of 30 degrees is 1/2. So the y component of the initial velocity is 8 meters a second. and I'm going to plug in t equals t sub f minus 1/2 times 9.8 meters per second squared times t sub f squared, and that when t is equal to t sub f, the y component is 0. So now we have an equation, it's a quadratic equation, which we can just solve for t sub f. So that's pretty straightforward. And so I can help things along a little bit by changing the order here. I'm going to write this as minus 4.9 meters per second squared times t sub f squared plus 8 meters per second times t sub f plus 2 meters is equal to 0. And this is a familiar form for a quadratic equation. The coefficient, this is traditionally called the A coefficient, the B coefficient, and this is the C coefficient. And if you remember your formula for the quadratic equation, you can just plug in and solve for t sub f. So there's that formula that probably got drilled into you in your high school algebra class. The solution to the quadratic equation says the times at which y is equal to 0 can be calculated by plugging in negative b plus or minus the square root of b squared minus 4ac all over 2a. And if you plug in the numbers, you get two different numbers corresponding to whether you choose the plus sign or the minus sign, and those numbers turn out to be either plus 1.85 seconds or minus 0.22 seconds. And clearly it's the plus value that we want because time 0 is at here. These are positive times. If you follow this trajectory back, there was a negative time at which the y coordinate was 0, but that's clearly not the one that we're interested in. So just as an aside here, let me tell you about a really useful tool that I think you will enjoy if you don't know about it already. It's the Wolfram Alpha tool, which you can access on the from your web browser. You just go to wolframalpha.com. And Wolfram is the company that makes the software called Mathematica, which is sort of a full-blown programming environment for doing mathematics. It's a really wonderful thing, although it takes a little while to learn because there's a lot of syntax that you got to learn. Wolfram Alpha makes it a lot simpler. It's a lot smarter, and it's particularly good at sort of doing algebra, for example, and making plots. So if you don't want to type into the quadratic equation, all you have to do is go into type in, if you don't remember the formula for the solution to the quadratic equation, if you just go to Wolfram Alpha and type in, you have to learn a little bit. You have to know that you have to type the word solve here, and then you have to know that when you want to raise something to a power, you have to use this caret. But other than that, it's pretty smart about figuring out what you mean. So you want to know the solution to this quadratic equation, and you type this in, and you hit enter, and it sort of interprets, makes sure that it thinks the thing that it's trying to solve agrees with what you wanted it to solve, and then it just gives you the results. And that's really wonderful. And this is in terms of square root signs. If you want a numerical answer, all you've got to do is click on this button here that says approximate forms. And if you do that, something like this will pop up. And then you can see down here the sort of exact solutions to the equation are given numerically. And not only that, but we're getting plots of what the left-hand side of this equation looks like. So you can really see that the left-hand side is equal to 0 when at times equal to minus 2.22 or plus 1.85 or so. But even more importantly, the quadratic equation is something where we have a known analytical solution. There's a formula you can plug into and get the solutions. But there are other equations that we'll encounter, and we'll encounter them pretty soon in which there's not a known, or at least not simple to find, analytical solution. And being able to get numerical solutions the way Wolfram Alpha can do is really quite useful. And also being able to see plots of graphs is really quite useful. So this is a tool. If you don't know about it, you should explore it. It's wonderful at doing calculus. It'll do integrals for you, all sorts of things. So check out Wolfram Alpha. So just to finish up the problem here, remember that the range, the horizontal range here, r, was equal to 8 times the square root of 3 meters per second. That's the horizontal component of the velocity times the time of flight, which we just found out was 1.85 seconds, and that comes out to be 25.6 meters, which is quite a throw. In fact, I believe it is a little bit greater than the world record in the shot put. The world record in the shot put is only, I think it's less than 24 meters or so. So maybe a slightly unrealistically high launch speed. If you could really make it travel 16 meters per second when it left your hand, you would be in the Olympics for sure. So that's it for this worked example. Hope to see you again soon. Bye bye.